Hello everyone. In the last lecture, we studied about the hydrograph and its various components and what are the factors that affect the hydrograph. Okay, so here in this lecture, I am drawing a hydrograph for a given storm, and we will study different techniques to separate the base flow from the hydrograph. Okay. So here in this lecture, we'll cover three methods based on your hydrograph, base flow separation. Okay, so let us discuss these all in detail.
So first method is your straight line method, in which what we do the base flow separation by intersecting a line between point A and point B. Okay, so what is point A? Point A represents the beginning of the direct runoff. Okay, so this is the base flow curve. Okay, and from here the your discharge is increasing very rapidly. Okay, so at this point this A, it represents the beginning of your direct runoff. So from this point your direct runoff starts. So it is very much easy to find this point, because we can see a very sharp change after this point. Okay, so what is point B? Point B is the end of your this direct runoff. Okay, so it might be very difficult to find this value, this point here on this curve. Okay, so we use an empirical equation here, so that is n equal to 0.83 a raised to power 0.26. okay, where a is your drainage area in kilometer square, and your n is the time interval from the peak to B to the point B in days. Okay, so this is your n, this is the point P, this is peak value, and this is point B, and what is the time taken between these two points? This is called your time interval, that is represented by n days. Okay, so we have discussed in the previous lecture about this curve, this your rising limb, and this peak, and the recession limb. Okay, so now so we are going to join these 2 points, that is point A and point B. First of all, we'll find this point, exactly this point B, and then we'll join the line from A to B. Okay, so this is the first method. By this method, what we do, we separate this base flow from direct runoff. Okay, now next method, in the second method. Okay, so in second method, what we do, the base flow curve, that is this curve, this is your extended till it intersect the ordinate that is drawn at the peak. Okay, so we extend this line and we extend this curve, okay, further to meet this line at point this point. Okay, this point is termed as C point. Okay, after that we join point C and B here. Okay, so this is the second method. So in this, the segment AC and CB, this AC and CB, they demarcate the base flow and surface runoff. Okay, this will be the base flow, and the above part will be your surface runoff. Okay, so this is probably the most widely base flow separation method that we use. Okay, so method number 3 is what we do in method number 3. We extend this curve. Okay, the point, the curve after point B, we extend this curve to the point, up to the point where it intersect this line. Okay, so what is this? This is your this line, this is your inflection point. Okay, so this inflection point line is going to be intersected by this curve that we are extending backward. Okay, so let it be the point be F. Okay, then we'll join this point by A through a smooth curve. Okay, so by this we can just separate your base flow, okay, from your direct runoff. So these are just these all the three methods. Okay, these are arbitrary methods. So selection of these methods, they depends upon the local practice and successful prediction which are achieved in the past experiments. And your surface runoff hydrograph is obtained after your base flow separation is done. Okay, and that runoff is called your direct runoff hydrograph, hydrograph. Okay, so next one is your effective runoff, effective rainfall. Effective rainfall, it is represented by ER. Okay, so what is this? This is the part of the rainfall that becomes a direct runoff. Okay, so it is thus the total rainfall in the given duration from which your abstraction such as infiltration and initial losses are subtracted. Okay, so we subtract your initial losses and infiltration losses, and then we find the value of your the rainfall, that is termed as your effective rainfall. Okay, so your ER could be defined as that rainfall that is neither retained on the land surface not infiltrated into the soil. Okay,
Let us draw a heatograph here. Okay, so that we can exactly define what is your effective rainfall and how we separate it out from the given heatograph. Okay, so it is very much important to study your effective rainfall heatograph. So let us explain it.
here this is the heatograph for a given storm that I have drawn here. So now your effective rainfall heatograph, that is obtained by pruning these losses from this heatograph. Okay, so for the given storm. Okay, so now the resulting heatograph after these losses are removed, that is termed as your effective rainfall heatograph. Okay, so now both your DRH and ERH, that is your, what is DRH? DRH is your direct runoff hydrograph, and what is ERH? ERH is your effective rainfall heatograph. Okay, so both these DRH and ERH, they represents the same total quantity but in different units. Okay, since ERH is usually expressed in your centimeter per hour, that is your ERH, so it is plotted against time. The area of ERH multiplied by the catchment area gives the total direct runoff. Okay, so what we do, we multiply the area of your ERH, that is effective rainfall heatograph, this the area of this effective rainfall heatograph by your catchment area, so that will give you the total volume of the direct runoff. Okay, so initial loss and infiltration losses are estimated that based upon the available data of the catchment. Okay, this is also termed as your phi index. Okay, so we have a certain procedure to calculate this phi index too. So these are your losses. Okay, so let us take an example on this.
So here we have a rainfall of magnitude 3.8 centimeter and 2.8 centimeter occurring on two consecutive 4-hour duration uh, on a catchment of area 27 square kilometer produced by following hydrograph. And we are provided with your data, that is time from the start of the rainfall and the observed flow in the catchment. Okay, so we need to estimate the rainfall axis and your phi index for the given numerical problem. Okay, so we have two storms here, one of 3.8 centimeter and second of 2.8 centimeter magnitude, and the duration for these two storms are your 4 hours. Okay, so let us let us solve the numerical problem.
So first of all, a hydrograph is plotted to a scale that is for the given your data. Okay, so let us draw the hydrograph first.
So here I am drawing the hydrograph for the given problem. So every time you will be provided with the data, that is the mass curve data. Okay, so mass rainfall data, so from which we need to first of all draw the hydrograph. Okay, to so that we can find out what is the time interval from where your direct runoff is starting in the given stream. Okay, so this is very much important because if we want to calculate the maximum discharge at the outlet of any stream, so we need to first of all understand what is the pattern of your direct runoff in that stream due to any storm. Okay, so it become very much important to first of all plot the hydrograph for the given problem area. Okay, so here let me finish this first. uh, so I have just fast forwarded the this video so that we can save some time here. Okay, so let me complete this first, then we'll discuss how we have plotted this hydrograph here. Okay,
So here is the hydrograph that we have plotted for the given numerical problem. So we have plotted this hydrograph to a scale here. So let us see first how we have plotted this hydrograph. So we have the data given here. Okay, so this is the time for the start of the rainfall, and we have observed flow in meter cube per second here. Okay, so how to make the hydrograph first? We have to take the time in at x-axis and your discharge at y-axis. Okay, so let us draw the hydrograph for this. So I have already drawn, so let us see the points. So here you can see the time from the start of the rainfall, it is given -6. Okay, and this is the time before the rainfall has started. Okay, so the rainfall has started after 6 hours. So before 6 hours after the rainfall has started, the observed flow is given as 6 meter cube per second. So here you can see we have plotted the observed flow before the rainfall has started in the stream has to be 6 meter cube per second. Okay, now moving forward, the rainfall has started from time 0. Okay, so here from here the rainfall has started. Now we have the observed flow in meter cube per second as 5 for 0, so we have plotted here 5, and after that for time for 6 hours we have observed flow of 13. So 6 hours we have observed flow of 13 here, you can see. And after 12 hours the observed flow is your 26, and then after next 6 hours it is 21, then it is 16, then it is 12, and then it is 9, and then it is 7, okay, and then it is 5, and after that the value here is for 54. After 54 hours the value is 5, and then 4.5, and then 4.5. okay, so these are the values. So we have plotted the hydrograph like this. Okay, so now we need to calculate. So this is your total hydrograph. We have your base flow in this hydrograph right now. Okay, so we don't know where is the separation point. Okay, so we want to separate the base flow from your direct runoff. So here you can see I have written the effect, the rainfall. So we have two storms here. Okay, so in the given numerical we have two storms of magnitude 3.8 centimeter and 2.8 centimeter. So this is your 3.8 centimeter and 2.8 centimeter magnitude storm. So we have plotted the storm here. Okay, and the duration is, one is of 4 hours and the other one is of 8 hours. Okay, so you can see here we are getting a curve like this. So this is your hydrograph. So we have, this is your base flow component curve, and after that from here this is your rising limb, this is your peak, and then after that it is declining. Okay, so we are getting the curve. So this is the recession limb. Okay, after that the flow is reaching to the base flow. So we need to separate this component. Okay, so I have written here the values. So we'll calculate how these values have come. Okay, so now after plotting the hydrograph for the given data, we'll use here the simple straight line method of base flow separation. Okay, so in that we use equation first of all to find the value of n. Okay, as I have discussed, so we'll use the equation n equal to 0.83 a raised to power 0.2. okay, so where a is the area of the catchment, it is given as 27, so we'll put the value here and we'll get the value of n. So it is coming out to be 38.5 hours. Okay, so but however when we do the inspection of this hydrograph, so you can see that DRH starts, that is this direct runoff, it starts at t equals to 0. okay, and it has a peak at t equal to 12 hours. okay, and it ends at t equal to 48 hours. okay, so which will give the value of n. If we calculate by this, we can get the value of n as 48 minus 12 equal to 36 hours. How? Because what is n? N is the the time duration between the peak and the end of the storm. So this is your n, this value is your n. okay, so we have calculated here, it is coming out to be 36 hours. So this is your more satisfactory in this case, so we'll take the value as this. okay, so you can check it by inspection or by using the equations. okay, so now moving forward, we'll calculate the area of DRH. Now we need to calculate the area of this curve. Now this is the base flow component here. okay, so this is your base flow, so which is starting at your discharge 5 meter cube per second. okay, so this is given to you, and this part, this is your direct runoff. So you need to calculate the the area of this curve. So it will give us the direct runoff here. Okay, so how will we calculate this? So I have calculated the area of DRH here as like this. So how I have calculated this, so I'll tell you. So here you can see in the curve, so area of this DRH, if we divide this curve into simple figures like this, so this is your first figure and this will be your second, and after that this, after that this, this and this. Okay, so we have divided the area into these small figures. Now we'll calculate the area of all these figures and we'll sum up all the values to get the total area of this runoff. Okay, so here you can see first figure is your triangle, last figure is also a triangle. So half of, we'll use the formula here, that is half of base into height. Okay, so what is base? If you can see here, what is base? Base will be this, and this is given as 6 hours. So half of 6, it is in hours, so we need to calculate it into minutes. So we'll calculate it as 6 into 60 into 60. Okay, so this is your base of this, and what will be the height? Height will be this. Okay, so this is your 5 and this is given as 13. Okay, so 13 minus 5, okay, it will give you 7. Sorry, it will give you 8. Okay, so we'll use the value here 8. Okay, this is how we will calculate the value of this first value. So in the similar way, we'll calculate the value of this triangle, and for this figure, this is a trapezium. Okay, so we'll calculate as half of base into sum of your non-parallel sides, this and this. Okay, so sum of this non-parallel side will be, so this is calculated as 8 plus, so we'll calculate this value now. Okay, so what will be this value? This is given as 26. Okay, and this is this value is 5. Okay, so it is 5, so 26 minus 5, it will give us 21. So this will be the area of this figure, the second one. Okay, so in the same way, we'll calculate this. We'll calculate first this, and we have this is 21. We'll calculate this. Okay, and after that this, and we'll sum them up to get the area of this figure. Okay, so here I have done the calculation work. So this 6 multiplied by 16 into 60, this is the base we have, because the base is common for every figure here. This is of 6 hours duration. Okay, so we'll take it outside and we'll sum up the values, remaining values. Okay, so half of this 8, so this is for this figure, first figure, and half of 8 plus 21, this is for this second figure, and then half of 21 plus 16, this is for this third figure, then half of 8 plus 21 for next figure, 21 plus 16, 16 plus 11, 11 plus 7, 7 plus 4, 4 plus 2, and half of 2. This is the last value. This is that triangle. Okay, so we'll calculate the area of the figure like this. So we have come up with the value as 1.49 into 10 raised to power 6 meter cube. So this is your total direct runoff due to the storm. Okay, so we have two storm values here. So one is your of 3.8 centimeter and the other one is of 2.8 centimeter. Okay, so we have two storms here of 4 hours duration. So total duration is of 8 hours. So we have calculated the direct runoff for this as this value. Now next we'll calculate the runoff depth for this runoff that we have calculated here. Okay, so the runoff depth will be runoff volume divided by the catchment area. Okay, so runoff volume is 1.49 into 10 raised to power 6 divided by area is 27 into 10 raised to power 6. So this is given in this area which is given to you. It is in kilometer square. So we'll convert it into meter square first. Okay, so now we'll have by solving this we'll get the value as 0.0552 meter. So this is the runoff depth. Okay, so changing it to centimeters, we get to 5.52 centimeters. So this is the rainfall excess. Okay, so here if I show you here, so we have calculated this direct runoff. Okay, so this is for 5.52 centimeter depth. Okay, so that's why I have written like here this. Okay, and you can see here we have two storms we have plotted here. So now next you can see here, so this is your total rainfall which is given as we'll calculate the total rainfall 3.8 plus 2.8, it will give you to 6.6 centimeters. Now duration is of 8 hours, so we'll calculate phi index. Okay, so phi index is your 6.6 minus 5.52. Okay, divided by 2 divided by 8. Okay, so 8 hours is the duration. Okay, so phi index is what is this phi index? Phi index is the this value. So this is your rainfall. If this is your rainfall, okay, so what will be phi index? Phi index will be this value. Okay, these are the losses. So we have calculated these losses to be 0.135 centimeter per hour. So total rainfall that was given to you was 3.8 and 2.8 centimeter duration. So here we have plotted this rainfall here also. So we have 0 to 4 hours. This is our 3.26 centimeter rainfall, and this is the value of phi index 0.135 centimeter per hour. Okay, so when we subtract the value of this phi index from here, so we get this value. This is your effective rainfall. Okay, so this is your 3.26 centimeter effective rainfall for your 0.024 hours duration, and after that this is your 2.26 centimeter rainfall after your losses, after the reduction of losses. Okay, so this is how we calculate the value of your how we calculate the base flow separation. Okay,
So this is all about the base flow separation technique from my side. In the next video session, I'll take a example problem on effective rainfall hydrograph. Okay. Till then, take care and thank you so much for listening. Thanks a lot.